Welcome to an exploration of one of the most profound challenges in science, the observer theory paradox. How do our theories shape what we observe? Can we ever see reality without the lens of our assumptions? Let's begin by understanding what this paradox really means. We need theories to make sense of what we observe in the world around us. However, our theories also determine what we even consider to be observable or meaningful. This creates a circular relationship. Theories shape observations, while observations are supposed to inform our theories. Thomas Kuhn, the philosopher of science, famously stated that data are never theory-free. Let me explain this with a simple analogy about colored glasses. Imagine you're wearing colored glasses. Everything you see is tinted by those lenses. The lenses are like our theories, and the world is reality. Here's a question. Can you ever know the true color of something if you cannot remove your colored glasses? This is precisely the observer theory paradox. We can never observe reality without some theoretical framework. Let's look at a concrete historical example of how theories determine what we see. In ancient astronomy, the Ptolemaic model placed Earth at the center with planets moving in complex circular paths called epicycles. The Copernican model placed the Sun at the center with planets in simpler orbits. Astronomers literally saw different things depending on their theory. The same celestial observations were interpreted completely differently depending on which theoretical framework astronomers used. Let's express this paradox more formally using mathematics. We can write observation O as a function of reality R and theory T. O represents what we actually observe or measure. R represents the objective reality that exists independently. T represents our theoretical framework or paradigm. The critical problem is that we cannot access R directly without going through T. So our observation is really the theory applied to reality, where T acts as a filter or transformation. Thomas Kuhn described how entire scientific paradigms can shift, changing what counts as a fact. When paradigms shift, what counted as facts in the old paradigm may no longer be considered facts in the new paradigm. Different paradigms, P1 and P2, produce different sets of facts, F1 and F2. Quantum mechanics provides perhaps the most dramatic example of observer effects. In the double slit experiment, whether we observe which slit a particle goes through fundamentally changes the outcome. Without observation, the particle exists in a superposition state. Psi equals 1 over square root of 2 times the sum of psi 1 plus psi 2. Upon observation, the superposition collapses to either psi 1 or psi 2. The act of observation changes reality. Even our measurement apparatus is designed based on theoretical assumptions about what we expect to find. Let's look at a concrete numerical example from statistics. In science, we often use p less than 0.05 as the threshold for statistical significance. But here's a question. Why exactly 0.05? Why not 0.06 or 0.04? The answer is that this is simply a theoretical convention, not a natural law. Our theory determines what counts as significant. This threshold creates a sharp boundary that determines what results we consider real versus random, purely based on theoretical convention. The observer theory paradox leads to a serious problem: confirmation bias. If theories determine what we observe, we risk only seeing evidence that confirms our existing theories. The probability of observing evidence E given theory T is greater than the probability without the theory. This means we're psychologically and methodologically predisposed to find exactly what we're looking for. So the critical question becomes, can we ever escape this paradox? One strategy is to maintain multiple competing theories simultaneously and see which one makes better predictions. By testing multiple theories T1, T2, and T3 against the same observations, we can at least compare their relative merits. Strategy 2 is to focus on prediction rather than explanation. A theory that makes accurate predictions is useful, even if theory-laden. We can quantify predictive power as the ratio of correct predictions to total predictions made. What are the practical implications of this paradox for how we do science? First, we must accept that pure objectivity does not exist. All observation involves interpretation. Second, transparency about our theoretical assumptions becomes absolutely critical. We must state our frameworks explicitly. Third, we should replicate findings using different theoretical approaches to verify they're not just artifacts of one framework. Using multiple methods that rely on different theoretical assumptions helps triangulate toward more robust results. Let's examine a contemporary example, the search for dark matter. We cannot directly observe dark matter, but our theory of gravity predicts it must exist based on galaxy rotation curves. According to Newtonian gravity, velocity should be proportional to the square root of gm over r. But observations show that velocity stays roughly constant with radius, not decreasing as expected. This implies dark matter mass must be proportional to radius, creating an invisible halo. But here's the question. Is dark matter real, or is it simply revealing a failure of our gravitational theory? The paradoxical answer is we cannot know without theory-independent observation, which may be impossible. Some scientists propose modified theories instead of dark matter. Mond theory modifies Newton's law with a function mu that depends on acceleration over a critical value, a zero. This graph shows how Mond predictions differ from Newtonian gravity at large distances, potentially explaining observations without dark matter. We have the same observations but completely different ontologies, one with invisible matter, one with modified gravity. This brings us to the deep philosophical issue at the heart of the paradox. Truth is not the same as empirical adequacy. A theory can match all observations without being true. Two completely different theories can make identical predictions, leaving us unable to determine which is actually true. This is called the underdetermination of theory by evidence. Data alone cannot determine which theory is correct. We can also understand this paradox through information theory. The mutual information between observations O and reality R equals the conditional information plus information about the theory it's. The problem is we cannot cleanly separate the signal from reality from the theoretical filter we're applying. The entropy of reality given observations in theory remains greater than zero. Uncertainty remains irreducible. No matter how much we observe, there's always residual uncertainty because our observations are theory-laden. Let's work through a practical numerical example to make this concrete. Imagine we're measuring the speed of light in a vacuum. We measure c equals 299,792,458 meters per second. However, this measurement already assumes several theoretical commitments. First, it assumes that space is Euclidean, at least locally where we're measuring. Second, it assumes time flows uniformly during the measurement. Third, it assumes light travels in straight lines in a vacuum. Our measured value is the true value times a product of factors from each theoretical assumption Ti. The question is, how do we know these assumptions are correct if they're required to measure c in the first place? This creates what philosophers call the bootstrap problem. Theories pull themselves up by their own bootstraps. They define what counts as evidence, then cite that evidence as support. We use theory T to gather and interpret evidence E, then use that same evidence to support theory T. It's circular. The logical structure is T implies E implies T, creating a circular reasoning pattern. Philosophers propose two main approaches to escape this circle. Foundationalism says there must be basic observations that don't require theoretical justification, forming a foundation. Coherentism says beliefs support each other in a web of mutual coherence, with no absolute foundation needed. Most working scientists are pragmatic coherentists, accepting that theories support each other without requiring absolute foundations. Experimental design itself embodies theoretical assumptions. Using multiple methods that rely on different theoretical assumptions helps triangulate toward more robust results.